And we're back, and we're going to look at some simple harmonic motion. And this is one of the, I guess, stranger, more complicated types of examples that we would tend to experience in the AP Physics. This is a case where we have something like a stick, which is lying on a horizontal surface. Okay, so it's not hanging from anything. It's not vertical. There's no gravity to worry about. But it's on like a tabletop. We're looking at a bird's eye view, and we have a spring attached to the stick. Okay, in this case it's a quarter of the way from the end of the stick. We have an axis of rotation up here at the top, so one end is kind of like hammered into the tabletop. And we're going to just displace this thing. We're going to pull it out to a fairly small angle, so that'll stretch the spring by a little bit. And when you let it go, the spring's going to make the thing oscillate back and forth. So, because it's a spring making this thing move, it's going to be simple harmonic. The force, this restoring force that we have, is proportional to the stretch, or the displacement. And by definition, that's what we have for simple harmonic motion. Now, this is also a case where we don't have linear motion. That the stick is actually going to rotate through that angle back and forth on the tabletop. Now we're also assuming there's no friction, so the only force acting on this thing will be the spring, and because the spring is causing a rotation and an acceleration, the spring is producing a torque. So let's go ahead and see how to handle this thing. We're basically trying to figure out what's the frequency and the period of the oscillation of the stick. Now because it's just rotation, we're going to be using torque equals I alpha. And the other part of this is, we have to ask, well, what's causing the torque? Well, it's the spring force. And the spring force is negative k times x. That's the force part. Now the r, we need a distance. That's the distance from the axis of rotation. And according to this, it's 3/4 of the length of the stick. But now we also need the sine of the angle between the radius line and the line of force. So that means we have the radius is the stick, okay, and then we have the spring, that's our line of force. Sorry about that. And so we need the angle between those two. So we actually need that angle. Now that's 90 minus theta, if we look at that triangle there. Okay, now the sine of 90 minus theta is the same as cosine theta. So we're going to have to keep that in mind. Okay. And the other part of that is actually what's x? Okay, now x is, we can write that in terms of this r value from the axis of rotation. See if this makes sense. I'm going to write down the spring constant. For x, I'm going to substitute in the distance from the axis. That's our hypotenuse of that triangle. That's 3/4 the length. And then that's going to be times the sine of theta. Okay, that's going to be multiplied by 3/4 again, L. And the sine of 90 minus theta is cosine theta. Now on the left-hand side, we have the moment of inertia. This is a stick rotating around one of its ends. So that's 1/3 ml squared times alpha. Okay, so obviously it's a little bit messy. Let's play with this a little more and see what happens, because as we do this, we can simplify things just a tad. Let's just go ahead and see what we get. And so we're going to have 9/16, strange fraction, times L squared, sine of theta times the cosine of theta. I'm going to solve for the alpha at the moment. Okay, let's find that angular acceleration. So we have to multiply this all by 3. And then we're going to divide it by ml squared. Okay. Let's see, now the L squares are going to go away. And let's see, that's going to be divided by m, and we have sine theta cosine theta. Now, this could look kind of strange, and if you think about this, I said at the start of all this that we're doing this for a small angle. Now, small angles are, I don't know, 5 degrees, something like that. And we have that so-called small angle approximation, where for angles as they get closer and closer to 0 degrees, in radians at least, the sine of the angle is approximately equal to the number of radians for that angle. Now, the flip side of this, for small angle approximation, when theta is small, as it approaches 0, the cosine of a small angle is approximately 1. Now look what happens when we make that approximation on what we have here. We have both a sine theta and a cosine theta. Now sine theta is approximately theta, and cosine theta is approximately 1. So we have constants here, multiplied by theta, we have the k over m, and in particular, if we want to try to figure out how all this behaves with time, if that's our goal, I'm going to rewrite the angular acceleration as the second derivative of your angular displacement. Okay, it's no different than saying that the linear acceleration, put this on the side here, is the second derivative of your linear displacement. Okay, it's analogous to that. So in other words, we end up with the equation for simple harmonic motion. We have the second derivative, we have a minus sign, we've got constants, and we've got our theta. Now, as we know with simple harmonic motion, if you want to describe an oscillating system, okay, a periodic system, mathematically, you need a periodic function. And that's either a sine or a cosine. So we can guess, for lack of a better word, that our position as a function of time is going to be whatever your maximum angle is that you start off at when you pull it and stretch the spring out, times either the sine or cosine. Let's just go ahead and use sine of omega t. Okay, we need a constant there. We need this omega to ensure that you get rid of the seconds. You can't have any units inside that argument there. Now we also know that the general equation, think of just a normal spring bouncing back and forth. The harmonic equation is, in general, something that looks like this, where the constant in front of the variable on the right-hand side, that's always going to be omega squared. Well, here's our constants on the right-hand side. So omega is actually the square root of 27/16 k over m. This is the angular frequency. Now this also is the same as 2 pi times the frequency in hertz. Okay, how many times a second is this thing swinging back and forth? Or you could even write this, since frequency and period are reciprocals, 2 pi over the period. Okay, so we basically have solved this thing already. We've got an angular frequency, which translates into frequency. So our hertz is 1 over 2 pi times the square root 27/16 k over m. The period is just the reciprocal of that. We've got, we could find the position as a function of time. We could take derivatives and find the angular velocity, we can find the second derivative and get the angular acceleration at any given time. But think about how this is all set up. It's really the important part. It's all based on torque equals I alpha. It's a rotational problem. Okay, we made the small angle approximation in order to make it and kind of force it into our simple harmonic equation, and then we can solve it. Okay, as far as what's causing the torque, well, we have our F. If we kind of think of torque as Fr sine of some angle. Our force is the spring force. It's a certain distance from the axis of rotation. And then we have the sine of the angle between the radius and the force. That was our starting point. So even though we have just a really strange kind of problem here, strange situation, we can still, if we take it piece by piece, step by step, we can get into a form that we know how to solve. Okay, so yeah, these are the types of things we call small oscillations. Okay, when things are displaced by a small distance or small angle in this case, we can make these approximations, and it's acting like a spring would. Okay? It's harmonic motion. I hope this helps. It's a little different type of problem, but until next time, we'll see you later.